Good morning, everyone. My speaker on, you can hear me? Okay. I always check because, I've had weird stuff this semester. Okay, so today is a review of the whole semester as much as I can. And I left out graph theory because that's the last topic that we talked about. So it should be freshest in your mind. So I have a few announcements. I don't know if I should wait a little bit before I jump in. What do you think? My clock says it's a little early. So if you guys have any questions, now's the time to ask. You can turn your speaker on or you can ask in chat. I guess we're good then. All right. So let me jump in. Um, so I've got sort of, let me go through the thing. First of all, an announcement. How long a note sheet? Is there a lecture Thursday? Good questions, folks. There's no lecture Thursday. Today is the last day, exam period. I think tomorrow they call a study day or something like that. And exams start Thursday. So there are no more lectures. This is it. Okay. Um, your final exam is Friday, this Friday. Okay. From 10:30 to 12:30 and submitted via Gradescope. You have the extra half hour there. Okay, so it's kind of like our hour exams, except you have an extra 80 to 120. Okay. Um, so this time is special. It's mandated by the university. Okay. I don't set it. You don't set it. The university has to figure out how to do exams for 20,000 students. And that's a matching problem. That's a graph problem, by the way. Um, and so this time is mandated by the university. Okay, what will the exam cover? It's the whole semester. That's what comprehensive means. Um, all the sections that were covered on quizzes 1 through 5, plus chapter 7, sections 1 through 4, the stuff you had homework on. Okay, if there was a section, let me say this way, every homework assignment indicated what sections the problems were related to. Those are the sections that are on the test, okay, on the final exam. So what about a cheat sheet, which I shouldn't call it that, but let's say I do. I'm going to allow you 2 because we got a lot of material to cover, and you are allowed 1 for each exam. The rules for hand-in are all the same. Okay, you got to hand them in. You got to do all the stuff that you normally do. Got to get them into Gradescope. Notice that's 1 p.m. Gradescope time before the clock ticks to 0. All right, are there any questions about that part? That's 2 sheets, front and back, yes. Okay, you're allowed 2 sides for a regular exam. You're allowed 4 for the final. Okay? Do we have solutions for homework as practice? No, you don't. What you do have is the next topic. Okay? We have extended office hours from tomorrow on. So the regular office hours, we have regular office hours plus. So if you look at this, all the way through Thursday afternoon, we have regular office hours. So I will remind you where to find them. Remember under modules where they have, I don't know, office hours or something like that under the information modules. There's the calendar, and these hours will be put on the calendar also. So what do we have? You're supposed to use the Zoom link for office hours for the teaching staff member holding the extra session. So on Wednesday, Peter is holding a question and answer, whatever, office hours from 9 to 11 a.m. If you have any questions on any of the homework problems or the solutions, go. I will hold my regular office hours from 1 to 3, and Ben will hold his regular office hours from 3 to 5. So there's 6 hours where you can come and ask questions. It is a Zoom office hour. It's not a review session per se. You can review anything you want, but it's one-on-one, unless several of you want the time together, in which case you can do that if you book it together. Okay, then you can tell whoever his office hour it is that the other person's probably in the waiting room, and you can say, could we both be in this together? That's okay if you book that together. Okay, you can ask anything you want. So Wednesday has 6 hours. Thursday, in addition to the regular Thursday office hours, we have 10 a.m. to noon, 2 extra office hours in the morning on Thursday, and 2 to 4 p.m. in the afternoon with James. So we have 4 extra office hours on Thursday before the final. So altogether, we're looking at 6 extra office hours in the 2 days, plus their office hours this afternoon and the regular office hours. And the exam is at 10:30 Friday morning. Don't leave it till Thursday night if you can. Take advantage of the office hours. Everybody wants to help you. Okay? So several of you can group together. There will not be a review session like previous quizzes. We figured that there are a lot of people that have exams during that period. So what we did is we added all these extra office hours so you can come in. Whatever questions you want. Remember, we gave you access to all the previous quizzes. It's under a module for this week labeled previous quizzes. And if you don't have the questions, if you didn't copy it down, you can get the PDFs of the questions on the 5 quizzes there. So what do you have that you can ask questions on that's written down already? You can ask questions on the 5 given quizzes. You can ask questions on the practice quizzes. There's 6 of them. I put out a practice quiz for chapter 7, just so that you'd have some ideas what's going on. And you have all the homeworks. So you have 6 homework assignments that you can ask any questions on. Plus, anything in the book is game. Any of your review problems that you go over. Okay? And yes, Kyle.
So I had 2 questions that just kind of deal with things leading up to the exam.
Yes.
Are we, just like the quizzes, are we going to get a template of what the exam problems?
Yes, you will get a template.
And is that going to be on Thursday or Wednesday that should come out?
Thursday at 3:00, I will have the template ready, both templates ready for you. Okay?
Thank you. And just like the quizzes, we aren't supposed to join a Zoom meeting or anything for this. It'll just be through Gradescope. The exact
That's right. We will have monitors watching Piazza for all your questions. I think that, did you feel that worked well before, that you had your questions answered rather rapidly? I hope. No answer.
I feel like that would always be useful.
I'm sorry?
I feel like that's always useful if you can get questions answered quickly.
You can get questions answered. What we try and do when we hold it during regular hours, when it's an in-person class, we have people who walk the hall where you're taking the exam so they can answer your question. Well, we can't do that now. So we have people who are watching Piazza for your questions so that they can answer them right away. And if there's a question a lot of people have, then we'll make sure that the answer is public so that everybody can take advantage of that. Okay? All right, remember there's 6 extra hours in addition to regular office hours. So take advantage of it. We tried to have enough office hours so that if you have, I'm sure you have other exams, but there are no exams on Wednesday as far as I know, which means you're studying. So take advantage of it Wednesday. And Thursday there are exams, but we have 4 extra office hours on Thursday for you to come in and ask questions. Okay? Take advantage of it. We want you to come in. We want it to be clear for you. Okay? Okay, what's the next thing? So the announcement, I put out an announcement last night about bonus homework 8. Okay. It will be on Gradescope. It will have all the information that was in the announcement if you don't remember it, but of course you can look at it. Okay. It's not really a significant homework. If you look at what it says to do, this year they've changed the evaluations, the course evaluations, so that they're buttons and we can see what that you've completed. There's a button that changes color and it says you've completed it. That's all we want. We don't want any information. You're supposed to, this is anonymous. Feel free to I hope, do constructive suggestions so that if we're stuck doing virtual classes again in the future, if this doesn't go away or if there's another disaster, that we can improve the material. As I hope you realize, I try listening to you the whole semester. This is the end, are the things that we can do better as far as you can understand. Okay, we listen. We try to listen at least. Okay, so remember 11:59 p.m. So notice that you have a whole week. It's going to be public tomorrow at 3 o'clock. It goes public on Gradescope. You have to, we don't care if you fill out your other course evaluations first, but this class, you should fill it out, take a screenshot of it, and then upload the screenshot to Gradescope so that we have a record that you did it. That's all you need to do. It's worth 1 point, and that may not sound very much, but if you're sitting there on an edge, a lot of people sort of end up saying, my grade point average is 89.5, including the final. Can't you bump it up? This bumps it up. This is something you can do to bump it up to go from the B+ to the A-. Okay? So please do it. Okay? It helps us figure it out, and it helps you with your GPA, and it's a full point right on top. It's not part of any other score. It just bumps your grade a whole point. Will homework 7 be graded before the exam? Because of all the extensions, it's pretty tight. Remember, we have students who need to study for their exams too. We are trying to have the homework graded by Thursday afternoon. That doesn't give you much time. I understand that, but students are under pressure. However, since the homework was assigned, you can come in and ask during office hours, you can ask questions about the homework and look and talk to whoever's the staff member manning the office hours, and they can answer the questions for you so you'll know from what you handed in. Don't hesitate. Do it. Okay? All right. So we want you to be able to ask questions. I understand. Now, someone says, oh my gosh, how many questions are going to be on this exam? You're covering the whole semester. Well, no one asked that, but I assume you were interested. So think about this. How many questions was I able to ask during an 80-minute quiz? And the typical answer was 7 or 8. Not the first one, but the last 4 was 7 or 8. So how many questions will I be able to ask on the final? It's only 20 minutes longer. So the answer will be, I'm sorry, hang on a second. What if, so I can ask maybe 10 questions, 10 major questions with maybe some parts, okay? So, and I'm covering 7 chapters of material. Okay, so someone asked, will anything not on the quizzes be on the final? And my answer is, remember on the quizzes, I could only ask, we had a lot of material in each chapter, and I couldn't ask a question on everything I thought was important. So I had to ask some questions on what I thought was important. That's going to be true now too. So not all of the questions will not be the same as were on the quiz. It may be on the same material, and there may be other things that we covered that weren't tested on the first quiz, on the first 5 quizzes that are covered. There'll definitely be something on chapter 7. Now, someone answered, when I enter a what if grade, of 1 for the bonus assignment. Well, don't worry about what Canvas does. We're changing Canvas. Okay. What you're doing is adding it into assignments or something. That's not where it goes. We're going to deal with it. It will be 1 full point. Okay. I understand what Canvas does. Okay. We have a way around Canvas. I promise. Okay. We will do it. If we do not do it, your GPA stuff will be right on Canvas and you can look at it and you can see what happened. All right. And you can come and ask questions. Have faith. Okay. I am not trying to horse you around. Well, on a mean score, why would it be? I have no idea. We haven't gotten there. You think the mean is 55? I hope not. According to Canvas. Well, I don't think Canvas is the ticket. And I have not been curving. Remember, we said at the beginning of the semester, we don't curve. You can drop your lowest grade. Okay. Yeah, that's pretty bad, but it may mean that no one studied. Okay. I have not looked them over in detail yet, but let me go on. All right, we have a lot of stuff to cover today. I understand you're all worried. I get it. I hope that's the one you get to curve. Okay. So here's my disclaimer. Okay. Slides today don't cover all the material from the semester, nor everything that could be on the final exam. They highlight some important material that is frequently misunderstood to try and clarify it. Graph theory is purposely omitted because we just talked about that for 3 classes. Okay, so let's remember predicates and propositions. A sentence that is unambiguously true or false is called a proposition. This is way back at the beginning of the semester. A predicate is a statement that has a variable, 1 or more variables, that when you replace them with values, they become propositions, unambiguously true or false. Okay, you should remember quantifiers. There exists and for all. And remember that in multiple quantifiers, order matters. There exists something for all something is different than for all something there exists something. So here's an example. If we say for all y and z, there exists an x and z such that x plus 2y equals 3. Okay, now what does that mean? That means that each x has a different y. And there exists a y that goes with each x. Okay, but if we say there exists a y and z for all x and z such that x plus 2y equals 3, that's not true, because that's saying there's one y that works for all x's. Okay, so that's something that can be very confusing, and I want you to try and remember it, and that's why there's an example of it right with the statement. Okay, so what else do we have here? We have, remember, negating quantified predicates, how to negate them. You go through that section. It's important. I'm pointing out some of these things, and I'll only pick a few things to do example problems on because we only have 1 class to do it. Okay. So remember, implications. We're still on chapter 1 here. Implications. P implies Q. That reads, if P, then Q. So these are logical, and there's a logical expression equivalent. Okay. So the truth table for not P or Q is the same as the truth table for P implies Q. That means that they are logically equivalent. You can replace one with the other. Remember, negation of it is P and not Q. So negation is not an implication. It's a logical expression. Yes, Lewis.
Quick question. On the last slide, you were talking about negating statements or quantified predicates.
Yes.
How do you, I know for equal, to negate it, it would be the equal sign through the slash, but how would you negate the less than equal to, or like the less than operation?
It less than becomes greater than or equal. Less than or equal becomes greater than. Remember, if something is not less than, then it must be greater than or equal, okay?
Okay.
Good. Glad you asked. Okay, remember negation, converse, inverse, and contrapositive. We use contrapositive all over in many of our proofs, so don't forget that. That's a biggie. Remember that in truth tables and in implications, this is so confusing that the hypothesis can be false and the implication can still be true. Okay, and in fact it is. So here's the truth table for implication. And notice that if the hypothesis is false and the conclusion is true, the implication is true. If the hypothesis is false and the conclusion is false, the implication is still true. Very confusing. Okay, but that's the way it is. So remember that. Okay, let's have an example. So here we have an implication. If 1 + 1 = 2, then 2 + 2 = 4. Is that a true implication? I have if and then. If P, then Q. Is 2 + 2 = 4? Yes. So the conclusion is true. Is 1 + 1 = 2? Yes. So this says true implies true. Is that implication true? And yes, the implication is true. So here I say 1 + 1 is 3. So that hypothesis is false. 2 + 2 = 4. Well, that's true. So I have written an implication. P implies Q, but P is false. Is the implication true? And the answer is implication is false. That's the truth table we just looked at. And in the last two, both of them have false hypotheses. The top one has a true conclusion, and the implication is true. False hypothesis, false conclusion, the implication is true. Okay, confusing, but that's life here. Okay, proving implications. What are the techniques and what kinds of things do we have? We had direct proofs and direct Britain. Yes, question.
Can you hear me? My mic has been
Not
bad.
very well. Your mic is really set low.
Okay, I'll just talk really loud.
Good.
On that second one, on the last problem, I thought that would be true for the implication.
No, that's the only time the implication is false. Oops, you're right. My brain is not working right. I think I wrote this wrong. There were only 3 of them. There were supposed to be 4. That's what my problem is. I left out one. You're right. That's what happens. If 1 + 1 = 2, then 2 + 2 = 5. Okay, so that's true, implies it's true, not false, implies true. The implication is false. You're right. I only copied down the 3 true ones. Thank you. There are 3 here. I meant there to be 4. Sorry. I meant to mimic the truth table. Whew. Thank you. You are right, Seth. You are right, Dave. You are right, Britton. I was wrong. Mea culpa. It's what happens when I do what I think is there, not what is really there. Okay. Proving implications. We had direct proofs. That was by construction, where we created it, by cases, by induction. They were all direct proofs. For indirect proofs, we have contrapositive. Remember that saying, if we prove not P implies not Q. Why is the contrapositive equivalent to the original implication? Does anybody remember why? How do you know when 2 logical expressions are equivalent?
When they're truth.
You look at the truth table.
Good, when their truth
Oh.
tables are the same. Absolutely. Good job. Good. So, okay. So the truth table for the contrapositive is exactly the same as the truth table for the implication. Okay, and contradiction is another technique. So what do we do in contradiction? We assume both P and not Q are true and follow the proof until we find the contradiction. And finally, a counterexample. Counterexample is very close to contradiction. In a counterexample, we're proving the implication is false by coming up with a valid example that has P and not Q. Okay? Good. All right, so here's an example of an implication proof. Use proof by contrapositive to show that if 3n plus 2 is odd, then n is odd. Okay? So what's the contrapositive? Well, the contrapositive is the negative of n is odd. So that means n is even. So if n is even, then the negative of 3n plus 2 is odd is 3n plus 2 is even. So that's our contrapositive statement. And since their 2 are logically equivalent, we have to just prove if n is even, then 3n plus 2 is even. So what do we do? What do we start out saying? Well, if n is even, n even implies n is equal to 2p, p in z by definition of even. We good on that? Good. So what does that mean? So then we substitute 3n plus 2 is equal to 3 times 2n plus 2. That's just substitution. And then what do we do? Well, if we're having every step says, well, that's equal to 3 times 2n plus 2. And that's, what is that? That's associative. And that's equal to 2 times 3n plus 2. What's that? That's commutative. What's that equal to? That's equal to 2 times 3n plus 2. What's that again? That's associative again. And that's equal to 2 times 3n plus 1. What is that? That's distributive. And what is that? That's equal to 2 times k. K equal to 3n plus 1 in z by, what is it by? It's by closure. Did I spell closure? God, I wish I could. closure of integers under multiplication and addition is even by definition of even. Okay, so it's a straightforward proof of the contrapositive. All right, let's move on. Okay, then proof by induction. Now, as you noticed in sets, not sets, I'm sorry, in graph theory, we had two really big uses. We had contradiction, contradiction, contrapositive, and induction were three of the big techniques that got used in proving things about graphs. So remember, what is proof by induction? That says you have to create the statement P of n. And what is P of n? P of n is a predicate. Why? Because n is a variable. And you want to prove it's true for all positive integers n greater than or equal to some integer b, the base case. Typically b is 0, 1, or something. The example we're going to do, b is 4. Okay, so it can be any integer, and we're going bigger. So we have to formulate the predicate. We have to prove the base case is true. We have to state the inductive hypothesis that says, assume in the strong induction case that P of B up to P of Mary minus 1 is true. They've been verified. And then you prove that PM is true. Usually you will get this by writing the desired property as some sort of recurrence relation. In the case of graphs, we wrote it by saying, well, I can remove an edge, and then I have a graph that has one fewer edges. So I can apply the induction hypothesis, and then you add it back in, or you do something. Okay. So you have to create this and find the recurrence relation. So here's an example. We use proof by induction to prove that 2 to the n is less than n factorial for every integer n where n is greater than or equal to 4. Okay. All right. So what's our P of n? What's
That
P
would
of
be
n?
basically just you're given 2 to the n is less than n factorial.
Yeah, it's almost all of it, not quite.
Oh, for n in the integers greater than or equal to.
N greater than or equal to 4 in Z. Yes, you need that piece. Okay, so that's our predicate. Okay, what's the base case? Well, what's P of 4? Not P of 1, not P of 0, P of 4. 2 to the 4th is equal to 16. N factorial is equal to 4 times 3 times 2 times 1, and that's equal to 24. So 2 to the 4th is less than 4 factorial, and P of 1, P of 4 is true. Okay? Good. Now, what's next? What's our inductive hypothesis? Our inductive hypothesis is that P of 4 up to P of m minus 1 is has been verified and is true. Now what do we do? Now we look and say, okay, 2 to the m is equal to 2 times 2 to the m minus 1. Okay. Now, what do we know about 2 times 2 to the m minus 1? Well, in particular, what do we know about 2 to the m minus 1? We know that the 2 can stay there, but I know that that's strictly less than m minus 1 factorial. You with me? They're both positive numbers, so I replaced one of the factors by a bigger number. So we have that. What else do we know? We know that's less than, we know that 2 is less than m, since, so this is the induction hypothesis for m minus 1, which we have as true. And the next one is true since 2 is strictly less than m. So I have replaced 2 times m minus 1 factorial by m times n minus 1 factorial, much bigger number. Okay, and this is equal to just m factorial. So we have shown that 2 to the m is strictly less than m factorial. Okay? All right, let's move on. Other proof techniques that we had. We had the big one, pigeonhole principle, which you've seen used in a variety of other circumstances. You saw it used in probability or combinatorics. You saw it used in graph theory. Okay, that's a big one. When you use the pigeonhole property, you can't just write n equals something and m equals something. You have to be clear, okay? You have to specify how you're applying the pigeonhole property, okay? In general, this is not just pigeonhole, but general proof techniques, okay, is to always use definitions to express things that reveal fundamental properties. Use variables to represent any element in the domain. Don't pick a constant and say, gee, it's true for when m is 3. That's not a proof. That's an example. Okay. You apply rules and properties that are true for every element in the domain. Remember, in our induction proof there, our domain started with m equal 4, integers bigger than or equal to 4. It wasn't all the integers. It wasn't all the positive integers. So be careful to use the correct domain. Finally, in that case, the resulting conclusions are true for any element in the domain, and you've done a proof. Okay, what else do we have? Okay, among 109 people, at least how many must be born in the same month? Defend your answer with a proof. So what do you think? What do we do? Well, we have the number of pigeonholes. We have I'm trying to find my formula again. M plus n objects, the number of objects. So we have the number of pigeonholes and the number of objects. So what are how many objects do we have?
109.
109. Thank you, Faze. 109. The people are objects for this case. How many pigeonholes do we have for them? Vista, very good, 12. Okay, so the pigeonhole property says that 109 is equal to 12 times Mary plus 1. Okay, or 12 times Mary equals 108. What's M? Oh, you guys don't do enough construction work. Okay. A 2x8, 2x4x8 is a standard beam length, and that's M equals 96. Whoops, that's no good. M is 12 times what? Well, a 2x4x8 is 8 feet long and it's 96 inches. So M equals 8. So how many people, at least how many people have the same birthday? By the pigeonhole property, at least M plus 1 equal to 9 people have the same birthday month.
Dr. Cohen, I think you made a calculation error.
I
Yeah,
did?
I think that means 9.
108 divided by 12 is 9, not 8.
Oops, you were right. Well, 96 was, so I got that wrong. I got 96 right. You were right. That's better. Is that better?
Yeah.
Good. Thank you. Well, I got to 96. I didn't get to 108. Okay. Good. Okay. Up to sets here. So if you remember, a set is a collection of distinct objects. Notice the word distinct. So if I look at the set, 1, 2, 3, 1, how many objects does it have in it? What is its size? Its size is 3. The fact that I wrote 1 down twice doesn't affect the size of the set. Okay? The number of elements in that set is 3. Distinct objects. Okay, for a set A to be contained in another set B, it means that for all the variable x's that are in A, they're also in B. That implication has to be true if you have one subset, one is a subset of another. For two sets to be equal, if you remember, you have to prove that they're each a subset of the other, and in which case they're equal. When you're proving sets are equal, you're doing 2 proofs. Okay. Remember, we have the operations intersection, union, complement, or difference, complement, the number of elements, which we write N of A, which is also equal to writing, looks like the absolute value of A. They're both read that. We had Cartesian products of sets, and we had the power set. Power sets are a big deal. Okay, what kind of properties were important? We had the inclusion-exclusion property. Okay, when did we apply the inclusion-exclusion property? We applied it when we were looking at unions of sets. Okay, so when we're counting the number of elements in a union of sets, when the sets overlap, then the part that's in both of them has been counted twice, once for each set. So you have to subtract it off. When you have more than two sets that you're looking at a union of, it becomes much more complex. Go look at it. What did we other properties we had? We had all the properties from Theorem 6 in section 3.3. Commutative, distributive, identity, negative, double negative, De Morgan's, universal bound, absorption, complement, negation. We looked at Venn diagrams as a way of illustrating sets. Notice you're illustrating. You're not proving anything with a Venn diagram. You're illustrating. And we learned about partitions of sets. What were the three properties of partitions? A partition is a collection of subsets of the original set with the property that each set in it, each part, is not empty. The intersection of the parts is empty. They're disjoint from each other. They have no elements in common. And the union of all the sets is, of all the subsets, is the whole set. The union of all the parts is the whole. Okay? Partitions are very important. The dual expression, remember, that's where you interchange intersection and union, an empty set with universal set. And what's the duality principle? Anyone remember what the duality principle is offhand? The duality principle holds, if you remember, for logical expressions. We had equivalencies, and we had the same kinds of equivalencies that worked for logical expressions. The duality principle, yes, Dane?
The duality principle, can't we use it to prove a dual expression? Or suppose we have some sort of expression, can't we transfer the problem to its dual,
that's exactly
prove the
what
dual?
the duality principle says. If you know that an expression is true, be careful, you can find an equivalent expression by forming the dual of it. That's what the duality principle says, okay? So if one is true, then the other, one is true if and only if its dual is true. And if you look at the statement of Theorem 6 in section 3.3, what you see is that the two columns are the duals of each other. Okay, so you can really just write one column and replace it, and in your brain say, well, I know what the dual is. So here's an example of a proof about sets. We're going to go on. Let's see, we're running out of time and I want to get through everything. So this is already in your, was this shown? Yeah. So what does this proof say? This says, given the set of all integers of the form 2n plus 1, those are all the odd integers, 2n plus 1, and their intersection with the elements of integers in the set 5k plus 4, those have some evens and some odds. That intersection is contained in the set of all integers of the form 10 times an integer Mary plus 9. Okay, so how do we prove that? We prove that using an element-wise proof, which we're going to go through again. What does that say? That says, given an x in that intersection, then what do you know about it? Well, you know it's odd for some n, and you know that it's of the form 5k plus 4 for some k. That's the definition of the intersection, it has both properties. So you can substitute them and you have something of that form. You can add 1 to each side and you get that. You factor them. And then here's the part that's more interesting. You get that 2 divides the right side. Now, 2 can't divide 5 because they're relatively prime integers. So 2 has to divide k plus 1. So k plus 1 is even. Okay. There you go. It's even. And so we arrange it, substitute it back in, and discover that x is equal to 10 times p minus 5 plus 4, which is 10p minus 1. So we can add and subtract 10 and then put it in that form. This add goes with that minus. This minus becomes part of the distributive law. If we take that, we end up with something of this form, plus, if I get rid of the parentheses, that's minus 10 plus 10 minus 1. So that gives you the 9. And that when we use the distributive law and to get 10 times p minus 1 and finish it off and show that it's of the form. What did we have to show? We had to show it was of the form 10 times an integer plus 9. All right. Good. So element-wise proofs. Remember, you always start out on an element-wise proof. When you're trying to prove one set is a subset of another, you start out and say, suppose I have an element in the smaller set and I have to prove it's then contained in the larger set. So an example says if A is a subset of C and B is a subset of C, that A union B is a subset of C. That's an example. Here's another example. To prove that A equals B, you have to show that A is a subset of B and B is a subset of A. Those are all element-wise proofs. Now, those aren't the only kinds of proofs. So remember, we had equivalent expressions in theorem, whatever. Here's an example. I'm going to skip this example, but you should have it in the notes. I'm going to skip it because I want to get to all the material. Okay, if we have time, we can come back. But I want you to notice something. Okay, this is the if. That's the then. We're saying that we have to prove A union C equals C. So that's proving that A union C is a subset of C and C is a subset of A union C. Okay, both directions. We have theorem 6. That's our biggie here. Notice the two columns. The second column are the dual expressions of the left column. Okay, so why don't we have that here? Well, here we don't have an operator, we just have complement. And complement isn't affected when we look at duals. The exam will not be focused on chapter 7. The exam will have questions from chapter 7 because they were never asked. Okay, it might have a slightly more weight than 1/7 of it, but I don't know. Will theorem 6 be provided on the exam? Well, what we have is theorem 2, I think, in chapter 1, theorem 6 in chapter 3, and another theorem about Booleans in chapter 3. And they're all equivalent. You go from one to the other. So you might have one of them provided and have to exchange them. And remember, this is the exchange. Thank you for asking that. Here we go. Okay. The operators and gets replaced by intersection, gets replaced by multiplication for Boolean variables. Or gets replaced by union, gets replaced by plus, and not gets replaced by complement, gets replaced by complement. Okay, if we go between them. There are special elements. C is contradiction. We can't use C as a Boolean variable when we're talking about sets because we're looking, if we're talking about going back and forth between logical expressions, then C always means contradiction. T is tautology. So those are special named objects. They get replaced in sets by the empty set and the universal set for the problem at hand. And in Boolean algebra, that's 0 and 1. Okay? So here's a problem. Here's an example. This is the Boolean algebra expressions. Okay, there's our Boolean algebra expressions for commutative, associative, etc. All of the issues. I only gave one column because the other column we know from dual. What's the dual of A times B equals B times A? It's A plus B equals B plus A. We replace times by plus. Okay. Yes. Okay. We have to have a break. We got our 5 here. You can ask anything you want, but we got a few minutes here. If you want to work on this example, that's good.
Professor, can I ask a question?
Sure.
I always have a problem with proving problems. What is the best way to study and prepare for them?
And what is the best way to what? I'm sorry?
To prepare for proof problems.
Practice, practice, practice. Do lots of them. Go through all the old homeworks and try and do everything. Go through the quizzes, go through problems in the book, and go to office hours to verify, to get help to make sure you understand what you're doing.
Okay, thank you.
Practice, practice, practice. It's like learning a foreign language. Proofs are a different language. Okay, the proofs that we have here, remember, proofs can be very hard. Okay. Fermat's last theorem, the 4-color problem, these are all things that years and years and careers were won and lost on trying to prove these things. So that's not anything that is in the category for you guys. But these are usually fairly straightforward kinds of proofs where you use the techniques that are at hand, and we're going to use them right here. Okay. Now, sometimes there's an observation that you have to see, and that one can be hard. I admit that.
Okay, thank you.
Okay. Okay, shall we jump in? Okay, so we want to prove if A plus B complement equals 0, then A plus B equals B. So we start out, we know what A plus B is. A plus B, that's part of what we're trying to prove something about. Well, what's that equal to? So I look at the hypothesis here. And I don't know what that is, but I know the dual of it, A times B complement, dual, okay? I'm sorry, not dual, complement is equal to A complement well, there are 2 steps there, but we'll come back to that. I'm throwing too much in at once. One thing at a time. Times 1. Let's look at 1. Why do I know that that's true? What rule is that? What property?
Identity.
Good. Okay, what's the next step? Well, the next step is to say, well, that's times 1, 0 complement. How do I know one is zero complement? Well, because it says so right here, complements. What's the next step? What's zero equal to? Well, A times B complement is equal to zero. So I substitute that in. So what's that? That's just substitution. We're given that A times B complement is zero. We're applying the given. Okay, now what are we going to do? We're going to use what we know about complement. That's A plus B. By the way, what do we know about complement? De Morgan, De Morgan, De Morgan. I have an operator. So what do we have? We have A complement. Multiplication becomes sum. B prime prime. And that's De Morgan. All right. Now what do we know? A plus B times A complement plus, what's B complement complement? It's B. And how do I know that? I know that from double negation. Double negative. There we go. Now what do we do? Are we at a loss? Yeah, we're kind of at a loss, but let's look up and down. I have B's, two B's there. Tell me, what's the dual of the distributive law? Well, it's right here. Look, I have an A here and an A here and two different things. So it's almost ready to apply the distributive law, but not quite. So first we have to apply commutative. And that's commutative. You notice when I did this chart, distributive is the only one I put both sets of properties in for, because sometimes people don't see that. So now I have the first is the same in both the sum of in here. So I say, well, that by the distributive law is just equal to A plus A complement, and that's the distributive. So what is A plus A complement equal to? Well, think about it in logical terms. That's A or not A. When is that true?
Always.
A, huh?
That's always true.
Always true. So what does that mean in Boolean? It means it's 1. Okay, so we have a rule here. Where's our rule? A plus
Negation, I think.
yes, thank you. I have trouble finding these things. So that's negation. Good. And then I write that that's equal to B. How do I know that's equal to B? Identity. Every step. We start out saying, okay, I plug that in. Each step I have something, a rule that I can use about equivalencies. Okay? Great. Okay, to chapter 4, we had function definitions. A function from a set A, the domain, to a set B, the codomain, assigns each value in A to exactly one in B. Okay, exactly one in B. It may use up all of B or it may not, but it definitely assigns every value in A exactly one value in B. We have the definitions of the inverse function and composition functions that form new functions. Okay, I don't have that stuff listed here. That's for you. So some of the properties that are important is, remember, onto every element of the codomain is the output of at least one element of the domain, at least one element. One-to-one says nothing in the codomain is the output of two different inputs in the domain. Okay, nothing. What that means is if you take two different values in the domain, they go to two different values in the codomain. Okay, and finally, the notion of one-to-one correspondence or invertible or bijection. Okay, that means it's both onto and one-to-one. And if you remember, there were rules for finite sets, what you know about the number of elements in each set when different things apply. So we have an example here. If R is one-to-one, then the function g with the rule g of x equals f of 2x is also one-to-one. So how would we start out that proof? We'd start out that proof by saying let x and y be in R such that g of x equals g of y. Okay, that's always how you start out proofs of one-to-one. Then, now what do we know? F of 2x equals f of 2y. Why do we know that? Well, that's just the definition of g. Whatever is the argument, we plug in. Now what do we know? We know that since f is 1-to-1, 2x equals 2y. What is that saying? Well, it's 1-to-1, so the arguments are both the same. It's the same. Then what's the last step? The last step is, well, then x equals y. Divide both sides by 2. Yes, Jane.
So this proof technique is proving the contrapositive of the definition of one-to-one, right? Because we start with the outputs being the same, then work our way back to saying that the inputs are the same.
Yes.
Thank you.
Okay. Put your hand down.
Sorry, I have one more question.
Oh,
If we are
okay.
able to prove it directly from the definition, so the contrapositive, this statement, is that
Well,
okay?
Yeah, sure. But that is basically the definition. What do we know? We know that the definition says that for x unequal to y, f of x is unequal to f of y.
Right.
Okay. So we did indeed do the contrapositive. Yes, you could do it directly, but usually that's harder.
Right. So only if we like sadness and pain.
So we usually start out saying, suppose they have the same value. And then we didn't say they were different. We just said, suppose x and y are in R. Then we prove they have to be the same.
Okay. That makes sense.
Okay.
Thank you.
Chapter 4. Remember, relation from A to codomain B has a rule to create a subset of A cross B. Some elements in A may not be represented in the first of the ordered pair. Some may be represented more than once. Similarly, some elements in the codomain may not be represented, or they may be represented more than once. So we talked about inverse relations. What are inverse relations? They're the ones where we flip the order. Remember, Cartesian product is an ordered pair in the case of 2, and the inverse flips it. And composition, that form new relations. We had properties of relations that were reflexive for all elements of the set. A comma A is in the relation. Irreflexive, symmetric, anti-symmetric, transitive. Okay. We had definitions of partial ordering, strict partial ordering, strict total ordering, and equivalence relations. We also have in chapter 7.4 the fact that you can tell when a relation is symmetric if you look at the adjacency matrix of the relation. How can you tell, and how could you prove it?
Does it
Well,
have to be a
remember-
symmetric matrix?
I'm sorry?
Does it have to be a symmetric matrix?
Yes, it does. Thank you very much. And how do we prove a relation is reflexive? Or what is the characteristic for the adjacency matrix of a reflexive relation?
Diagonals only. need to be there.
Diagonal is not 0, it's 1. If you have a relation whose adjacency matrix, the diagonal has some 1s and some 0s, it's neither reflexive nor irreflexive. If it has all 0s, it's irreflexive. Okay? Good. Okay. So prove or give a counterexample. If R is an anti-symmetric relation, then R composed with R is an anti-symmetric relation. Okay, well, we have a counterexample, so it's not true. If A equals A transpose, that is the definition of symmetric also, so you're both right. Okay, so in this simple example, we see that we have 1, 3, and 3, 1. That's nice in the composition. But we have 1, 2, and 2, 1. That's nice. But we have 3, 2, but we don't have 2, 3. So it's neither symmetric nor anti-symmetric. Okay. Chapter 5. Okay, so we're getting close here. So remember, this chart is our biggie. We have 4 different kinds of things when we count. Okay, if we have no repetitions allowed and order matters, it's a permutation. If we are allowed repetition, but order and no order matters, then it's an ordered list. If we are allowed repetitions and no order matters, then it's a bag. And we had examples of bags. And if we are not allowed repetition, but order doesn't matter, then it's a set. Remember, if it's not allowed repetition, then we can think of elements in the set, but it can't, if order doesn't matter. Remember, in a set, order doesn't matter, there's no repetition. So those are the straightforward things. We had the sum rule and the sum with overlaps. Inclusion-exclusion principle becomes important. Okay, if you have sums with overlaps, you want to get rid of counting it twice. We had the product rule. We had complements. We had permutations and combinations. And then we have this biggie. This biggie says the following are equivalent and have the answer C of R plus N minus 1. Choose R. The number of unordered lists with repetition, what's that? That's a bag of length R from a set of N. The number of non-negative solutions to the linear equation x1 through xn equals R. The number of binary sequences of length R plus N minus 1 with exactly R zeros. That means exactly N minus 1 ones. And the number of bags of R atoms with N of N types. Okay, remember we can make a binary sequence out of any of these bags. The ones represent separations between the items. Okay? You're to buy 3 dozen bagels from a shop that sells plain everything, whole wheat, cinnamon, raisin, and blueberry. How many ways can you perform the task? What's R? The number of things you want to put in the bag. So that's 36. What's N? How many different kinds of bagels are there? It's a normal it's a normal dozen, not a baker's dozen. Okay. So we have 1, 2, 3, 4, 5 kinds. So the number of ways you can perform the task according to our rule is, okay, R N minus 1, oops, that's 4, comma, R, which is the number of ways of choosing 36 things from 40. It's a big num. If you throw in baker's dozen, you replace 36 by 39. Okay? Good. That problem is always a fun problem. Okay, here we have one more example. How many license plates, numbers only, consisting of the 6 digits out of the 10 digits from 0 to 9 with exactly 2 of the same digit are possible? Exactly 2 of the same digit are possible. Does order matter in the license plates?
Yes.
Yes, order matters in a license plate. Very good. Okay. So we don't know which digit wants repetition, do we? So how many choices for the digit to repeat do we have? How many choices for the repeating digit do we have? How many choices for the repeating digit?
10.
Good, 10. Okay. Now, how many choices we have for the 2 locations to put the digits in? How many choices for the 2 locations? How many choices do we have for the 2 locations to put the digits in?
Since order doesn't matter once you have 2 of the same digits, then you do 6 choose 2.
Good. 6 choose 2. Very good. Okay, now what?
So there's the 6 factorial.
I'm sorry?
So there's the answer is 15.
I'm
Go
sorry,
to-
I cannot hear you very well and I don't understand it. I apologize.
Okay, that's fine. I just
Let-
so
How many digits do we have left? How many places do we have left to fill in?
4.
4. We have 4 digits. How many choices do we have How many different digits can we choose from for those 4 places?
9.
9. Does order matter? Yeah, it's a license plate. Order matters. Are we allowed repetition?
No, because then that would ruin the exactly 2 with the same digits condition.
Yes, no repetition. Very good. So what does that tell us? That says permutations of 9 things taken 4 at a time. So now we have all the pieces and we put them together. Okay. Do I add them? Do I multiply them? Multiply, someone says. Good. So the number of license plates with the right rule is equal to 10 times 6 choose 2 times permutations of 9 things taken 4 at a time. That's it. Okay, I almost got to the end of this stuff. We have probability. Okay, so we define the sample space, the successful outcome, the probability. Look in our last example. Okay, let's look at our last example. What was the sample space? It was the set of all possible license plates, right? All possible 6-digit license plates was our sample space. Our event was having exactly 1 digit repeated twice in the license plate. So that's our event. And the probability of that event is the number of successes, number of possibles, divided by the number of elements in the sample space. We had the complement, we had the Bernoulli trials, random variables, and expected values. There will be questions on that. If you didn't understand it, if you had a problem on quiz 5, go to office hours. Okay. Here's our what's probability the license plates will have exactly 2 of the same digits. The same problem as before, but now we're asking probability. So we have the probability of the event E is equal to the number of elements in E over the number of elements in the sample space. The sample space, we have 10 to the 6th. We can have any digits in any places, repeated in any ways. Okay, it's ordered, but we're allowed repetition. What was this number? It was 10 times combinations of 6 choose 2 times permutations of 9 choose 4. 9, not choose. 9 things taken 4 at a time. And that's the probability that the license plate will have exactly 2 of the same digits out of all possible 6-digit license plates. Good. I think we're done. So I had a few more examples. Do them, fill them out on your own, bring them to office hours if you have any questions. And please come to office hours. I want you all to do really well on the final. I'm sorry if you had trouble on the last quiz, but please come to office hours and ask questions. We want you to do well. We can't do it for you, but we can help you learn it. Dane, yes.
Should we study Prim's spanning
I'm sorry,
tree algorithm?
what?
Should we study Prim's algorithm for graph theory?
You know, spanning trees are important, and Prim's algorithm is an important algorithm. I look at the problems as follows. I might ask you something about them, but doing an example with either a spanning tree algorithm, like to find the spanning tree of any sizable graph, a connected graph, could take quite a while. And I can only ask you a certain number of questions. So I am trying to not ask you a question that's going to take up an inordinate amount of time. So if you're asking me, do you have to know Prim's algorithm? I would say you got four sides of a cheat sheet. If you ask me what kind of question I might ask you about it, A, I haven't said it'll be on it, but B, remember we have a lot of stuff to cover on graph theory. And to be honest, I can probably ask maybe 2 questions out of the whole exam. So, I can't ask you something that's going to take you a half hour and have no time left for the rest of the exam. So,
Well, that helps. Thank you.
okay, I'm trying to tell you, you need to be able to know it to be able to answer certain kinds of questions. And I did an example for you to work it out, but just remember that if it takes you 15 minutes to do it, then I can't ask you much of other stuff. So maybe I could ask that, but then I'd have to cut down on other stuff that I asked you. Okay. There are lots of stuff that are important, and I'm trying to see that you understand it, but not kill you. And thank you for coming to class. I hope that you are going to do well. Please come to office hours. Please ask questions. And if I don't get to see you again or talk to you again, do well in the rest of your careers. I hope you enjoy computer science, because I've had a great career and love it. So I hope you love it too. There are lots of fun things. There is always stuff you don't like in any job, but just go for the nuggets of stuff you do like. And I'm glad you like the TA. Please fill out the evaluations and please put nice comments like that. We love them, but any helpful things that work. And evaluating the TAs that are helpful helps them as well. Okay? Is 3100 similar to this class? I haven't paid attention. It is not, but you're expected to know the material in this class. James, what is 3100 per se? I don't remember.
I'm not sure.
Oh, sorry about that. What is 3100? Who asked that question?
Models of computation. So they do a lot of
Theory.
And a lot of stuff that I don't understand, like specifying languages that just have a bunch of A's and B's and C's in them.
Well, I hope you will understand it. It sounds like fun to me. But just take everything you've learned in this class and don't be intimidated. Just work on it every night, piece by piece, and you will all do really well. A little bit at a time, lots of different times. Just the same way you learn. Remember, it's a foreign language and you have to learn it. Don't expect to get it overnight. All righty? Any questions? I'm here. Well, thank you all for coming.
Quick question. When's office hours again?
It should be, if you look at the stuff I posted, remember these slides are already online. They're listed under the review, the class review for this week. They are online for you. But I go back to the beginning and show you. Here they are. So all the regular office hours plus these, and they will be listed under the calendar for office hours as well. We haven't done it yet.
All right.
But
Well, thank you.
Get help, study, do well.
Okay, thank you.
I have a
My
question.
pleasure.
I have a question as well.
Yes, Alec.
So some of the grade scope rubric for quiz 5 said what the correct answer was, and some didn't. If I go to
Yes.
office hours and ask about a specific problem, will the TA help me arrive at a correct solution?
Yes, go to office hours. Exactly. We
Cool.
don't like to just give you the answer. We like to help you work your way through it and figure it out yourself. So we might ask you, what does that tell you and stuff like that. But yes, the whole idea is to help you learn. So yes, he will help you through it and you will get to the right answer. He or she will help you through it and you will get to the right answer.
Okay. And then also there's a couple places, at least one place in my test where my answer was a simplified version of the officially correct answer, and I got it marked wrong. I'm assuming I can reach out about that.
Within a week of receiving it, absolutely.
Okay, thanks. All right, thank you. Bye.
Any other questions?